So to do the calculations for this Mann-Whitney U-test, we're going to go to the Excel workbook chapter 10 and the worksheet Mann-Whitney U-test. And we're going to enter our two samples of data over here in the yellow cells. As always, yellow cells are cells that we can change. Green cells are automatically calculated. So here's the data from my placebo. Here's the data from my new drug. And then the Mann-Whitney U-test is done by ranking the data values. So it's going to take all these data values and basically line them up from smallest to largest. The smallest is going to get a rank of 1. So here's a rank of 1, and that corresponds to this data value. The next is going to get a rank of 2. So here's the next smallest, that has a rank of 2. Here's the next smallest, it has a rank of 3. And then data value 4 appears twice, so both of those values get a rank of 4.5, and so on and so forth. The book talks a little bit about the strategy behind this, but it's all built here into this worksheet. Over here, it calculates N1 and N2. Those are our two sample sizes. Now, those numbers are going to be important here in a bit when we talk about the critical values, so keep those in mind, our two sample sizes. Here, these calculations are kind of intermediate calculations, and in the end, we get a test statistic. It's denoted U, and it equals 3 in this case. So now, to decide whether we're going to reject the null hypothesis or not reject the null hypothesis, we're going to use the traditional method and compare that test statistic to a critical value. That critical value comes from Table 5 on page 282 in the textbook. We'll look at that table here on the next slide, but let's talk about what we're going to do with that first. And so remember that this Mann-Whitney U-test is always a two-sided test or a two-tailed test, and we're always going to use the default significance level alpha equals 0.05. Now, once we get the critical value, here's what we're going to do with them. The criteria are, say that we reject the null hypothesis if the test statistic is less than or equal to the critical value. And we do not reject the null hypothesis if the test statistic is greater than the critical value. So we're going to compare our test statistic to the critical value. If the test statistic is smaller, then we reject the null hypothesis. If the test statistic is larger, then we do not reject the null hypothesis. So here's Table 5 from the back of the textbook, and we see the title there, Critical Values of the Mann-Whitney U-test. This says for a two-sided test at alpha equals 0.05. Across the top we have values of N1. That's the size of our first sample. And then across the left-hand column we have N2, which is the size of our second sample. And then notice that this criteria down here says that we need N1 to be less than or equal to N2. And in this case, N1 and N2 are the same, they're 5. And so here we've got N2 is 5, N1 is 5, and so we're going to find the corresponding critical value, which is given right there. So there's our critical value 2. Okay. And so there's our critical value 2. There's our criteria again. Now our test statistic was 3, and so we compare that test statistic to the critical value. 3 is bigger than 2, and so we have our second part of the criteria, and so we would not reject the null hypothesis. Okay, so the null hypothesis was the statement that there is no difference between the two treatments, and so that means we would conclude that there is not a statistically significant difference between the two treatments. There just doesn't appear to be much difference. So kind of informally, this means that the treatment just doesn't appear to be effective. Our next hypothesis test is called the sign test. And the sign test, the purpose is to analyze data that come in matched pairs. Now, this test is going to be similar to the paired t-test that we talked about in Chapter 7. Paired t-test was used to also analyze data that come in matched pairs. Sign test, we made a claim about the mean of the population of differences. In the sign test, we're going to make a claim about the median of the population of differences. Okay? So the formal null hypothesis in a sign test is that the median of these differences is 0. So it's going to be like mu sub d equals 0, although our parameter isn't going to be mu sub d. And the formal alternative hypothesis is going to be one of three statements. Either the median difference is not 0, greater than 0, or less than 0. And so it could be any one of those forms. And so this illustrates that a sign test could be a one-tailed test or a two-tailed test. It's two-tailed if the alternative is not 0. It's a one-tailed if it's greater than or less than 0. Okay. So to illustrate an application of the sign test, let's look at example 10.4 from the textbook. And in this example, we're testing a new autism treatment. And we enroll eight children in our study, and each child records the number of repetitive behaviors before treatment and after 1 week of treatment. Okay. And so here's the data. Child 1 had 85 repetitive behaviors before treatment, and then only 75 afterwards. Child 2 had 70 before treatment and 50 after treatment, and so on and so forth. And so looking at the data, it looks like for most children they had more repetitive behaviors before treatment than they did after treatment. Here's one exception here, but so it looks like the treatment is effective. Okay. Well, let's look at how we could test this claim using the sign test. And let's make a couple of observations here. So if the treatment is ineffective, then the differences, if we take the number of repetitive behaviors before treatment minus after 1 week, then those differences would tend to be 0. So if ineffective, then there just wouldn't be any difference between before treatment and after 1 week. So these numbers would tend to be the same, so these differences would tend to be 0. Okay? Now, if the treatment were effective, then the differences would tend to be positive. If effective, then we'd have more repetitive behaviors before treatment and fewer after treatment, and so these differences would tend to be positive. Okay? And so the formal hypotheses that we're going to test here are that the population median difference is 0, and the alternative is that the population median difference is positive. So in what we're claiming, the null is the statement that if we took the differences from every single child who is on this treatment and lined them up from smallest to largest, then the number in the middle would be 0. The alternative says that if we lined all these up, then the number in the middle would be positive, or stated in other terms, that more than half of our subjects would have improved symptoms. Okay. Now this is going to be a one-tailed test because the alternative is that the difference is positive. Positive means greater than 0. So this is technically a right-tailed test, but it's generically a one-tailed test. Okay. Kind of informally, our hypotheses are that the treatment is ineffective versus the treatment is effective. So to do these calculations, we're going to go to the worksheet sign test, and we're going to change the numbers in the yellow cell. So we're going to enter our pairs of data, and so there's the pairs from the first student or the first subject and then the second subject and so on and so forth. And in the sign test, what we do is we calculate the difference of those numbers in each pair, very similar to the paired t-test. But now in the sign test, we identify each of those differences as either positive or negative. If it's positive, then we're going to put a plus sign here. If it's negative, then a negative sign, and so on and so forth. And so when we do the sign test, we're only really dealing with this list of plus and minus signs. The actual values of these differences are totally wasted. This is what we mentioned back at the beginning of this lesson. We said that parametric tests often waste information. In a sign test, we waste the magnitudes of these differences. All we look at are the signs. And then to do come to the test statistic, we count the number of plus signs, the number of minus signs. The test statistic is the smaller of these two numbers, and so it's 2. Over here we enter the number of tails. This was a one-tail test. And now for this type of hypothesis test, we calculate a p-value. We could calculate a p-value in any hypothesis tests. Some of them, the p-value is very complicated to calculate, and this one is very simple to calculate, and so I built that into the spreadsheet. And so there's our p-value. Now we're going to interpret that p-value in the same way as every other p-value. We're going to compare that to the significance level alpha. In this case, the p-value is much greater than alpha, and so we would not reject the null hypothesis. Okay? And so the null hypothesis was the statement that the treatment was ineffective, and so that means the treatment appeared ineffective. Our next hypothesis test is called the Wilcoxon sign rank test. Wilcoxon is the name of the statistician who developed this test. And the Wilcoxon signed rank test, its purpose is also to analyze data that come in matched pairs. So it's similar to the pair t-test, and it's similar to the sign test, but it's going to have more power than the sign test. The Wilcoxon signed rank test does not waste as much information as the sign test, and so it's going to have more power, which is good. So to illustrate an application of this, let's look at example 10.6 from the textbook. And this is the exact same scenario as what we just looked at in example 10.4. So we're going to use the same data, same scenario. We're just going to test the data with a different hypothesis test. So as before, the null hypothesis is that the median difference is 0. The alternative is that the difference is positive. And again, this is going to be a one-tail test because in the alternative hypothesis we have a greater than 0. Okay. And so the worksheet to do the calculations here is called the signed rank test. We enter our data here. This is the exact same data from example 10.4. It calculates the differences here. So it starts off the same as the sign test. And then it takes the absolute values of the differences, and then it ranks these absolute values from smallest to largest. And so this is the smallest difference. It gets a rank of 1. Now we have a couple of differences of 10, and so they get actually we have 3 differences of 10, and so they each get a rank of 3. And then we put the signed rank, which is simply where we take the sign of the difference and put that with the rank. And then we add up the positive ranks to get this W plus. We add up the negative ranks to get this W minus. And then the test statistic is basically the smaller of these two numbers in absolute value. So we have n here is 8. We have 8 pairs of data. We're going to need that here in a minute. And then here's our test statistic 4. So we're going to come to the technical conclusion using the traditional method, and our critical value comes from table 7 on page 285 of the textbook. And here's the criteria that we're going to use for coming to the technical conclusion. We're going to reject the null hypothesis if the test statistic is less than or equal to the critical value, and we're not going to reject the null hypothesis if the test statistic is greater than the critical value. So here's table 7. We see it's titled Critical Values for the Wilcoxon Signed Rank Test. And so we have two options, either a two-sided test or a one-sided test. In this case we have a one-sided test, and so we have different values of alpha here. We'll always use the default of 0.05. And then along this left-hand column we have the value of n. That's our number of pairs of data. In this case we have 8 pairs of data. So we're going to use that row and this column, and so our critical value is going to be 6. There's our critical value of 6. Again, here's our criteria. In this case, our test statistic was 4. 4 is less than or equal to 6, and so by our criteria we are going to reject the null hypothesis.